Welcome to NPTEL online course on fractals and multifractals. In the last lectures, we have discussed the deterministic fractals, in the sense how to define the Hutchinson mapping on the hyperspace and generate the fractal based on the Hutchinson mapping. There are few things which we need to note down. A deterministic fractal, that means the attractor will vary based on the iterated function systems. If one can change the metric space, then they will get the different type of attractor. In the same metric space, if you change the contraction mappings, in that case also one can get the different type of attractors that we have discussed with the example. Whereas, while discussing the history of fractals, we defined fractal in two ways. With respect to the self-similar property, the fractal is classified into two types. One is the random and one is the regular fractal. The set has the exact self-similar nature is called the deterministic fractal. An object which has the approximate self-similarity is called the random fractals. Now, in the previous construction process, we have seen how to generate the deterministic fractal in a metric space. Now, the question is it possible to generate the random fractal through the mathematical way? Yes, it is possible. Now, we are going to discuss how to generate the deterministic fractal which has some partial self similarity, not exact similarity. For this, let us recall what is the deterministic fractal which we generated in the last lectures. These lectures we are going to discuss Collage theorem, then algorithm for generating the fractals with the self similar nature of two types, random and regular self similar natures. Let us recall how we generated the fractal in the metric space, that means the exact self similar, so that we can call it as the deterministic fractals, because the each set is written as a finite copy of itself. Now, we are taking the X is a complete metric space with finite number of contraction, with maximum contraction is S, the iterated function system with the contraction factor is S. S is the maximum among the contraction of Wn's, where W is the mapping from H of x to H of x is defined by taking the union of all this contraction. Then we proved that this W is the contraction mapping on the complete metric space, this one with the contraction factor S. Then, as per the Banach fixed point theorem, this contraction mapping F has a fixed point, that fixed point we can write it here. This fixed point we can call it as the deterministic fractal. So, if we have the iterated function system, we can generate the fractal, it is a deterministic fractal. Why? A is written as a finite copy of itself, all finite exact copy of itself. Now, let me define what is the condensation set. Let x comma d be a metric space and A belongs to H of x. Here, without loss of generality, we can take the x comma d as the complete metric space and A belongs to H of x. Obviously, A is a compact set. Define a transformation W naught from H of x to H of x by W naught of B equal to A. We need to define a mapping W naught for all the element in B, the image of B under this mapping W naught will get the set A. See, if every element of B in H of x is a compact and this map maps this set to A, then W is called the condensation transformation and A is called the associate condensation set. A is a condensation set and W naught is the condensation transformation. One can note that all the Bi's are compact and A also compact sets. Now, I define what is the hyperbolic iterated function system with the condensation. Usually, the iterated function is a set x together with the finite set of contraction mapping, n number of contraction mapping. The iterated function means we need to say what is the contraction factor S. So, if W1, W2, Wn has the contraction S1, S2 up to Sn, you can take the maximum among all, that is a S with the this IFS, hyperbolic IFS with contraction factor S you can consider. Let define W naught from H of x to H of x be a condensation transformator. We have the definition of condensation transformation. W naught is the condensation transformation. Then among this finite number of contraction, we are adding this condensation map in the finite number of contraction. Then this IFS becomes the hyperbolic IFS with the condensation in terms of condensation set and condensation transformation with the same contraction. There is no change in the contraction factor. So, this IFS we can call it as the iterated function system with the condensation. Now, we know that if we have the iterated function system on hyperspace of X, we can generate the fractal by using the Hutchinson-Bansley mapping. For example, if this is the given mapping for us, that means if we define f of from H of x to H of x, f of B, if we are defining union of I equal to 1 to n W I of B, then this is the Hutchinson-Bansley mapping on H of x. This each W i's are contraction mapping. Therefore, this F is contraction. As we know, this F will give the fixed point on this complete metric space whenever X is a complete metric space. We will get the attractor, that attractor we can call it as the A star, that f of A star will satisfying the A star. For this iterated function system, that means without the condensation map X with this W I, where I is from 1 to n, it has the attractor like this one. Now, we have the one more iterated function system with the condensation set. What will happen if we add this condensation mapping on this iterated function system? Let us explain with the example, because this is also iterated function system. Will it generate the deterministic fractal? That means the attractor? Yes, it will generate. Then what is the nature of the attractor? That nature can be explained through some simple example. Take X as a real number systems, X with the R, that means X comma D is a usual metric space. That means X as a R we can take, R with the usual metrics we can take, and define the two mapping F1 and F2 on R. Here we can define F1 and F2 is defined as x by 2, F1 is defined as x by 2 and F2 defined as x by 2 plus 1 by 2. Now, if you are defining this one here, then we will get the attractor, because F1, F2 both are contraction with the contraction factor 1 by 2. Therefore, if you are defining the F, that means the Hutchinson mapping for these two mapping, F of A is defined as union of I equal to 1 to 2 Fi of A. If you are taking any set from this R, then finally maybe if you are taking the set 0, 1, yes, we need to take this instead of R, we can take 0, 1. If you are applying this mapping here, this has an attractor, that attractor is the closed interval 0, 1. 0, 1 is the attractor for this mapping F. Whereas now we need to define one condensation set. So, take the condensation set C equal to 2 and then the attractor A satisfies A equal to F1 of A union F2 of A union C, because in the IFS we are adding the condensation mapping, that means the condensation set will add, that means we need to find the mapping such that this mapping will map to the set A, we are adding the set A here, the image is C, we are adding instead of A we are adding the C. That means for this attractor this number 2 will be added, for the A we are adding C. Here the observe that starting from 2, repeat application of the map gives, you can see here F1 of 2 you will get 1. If you are applying this one on F1, these two maps, if you are applying F1 on the C, one can get F1 of 2, one can get as 1 and F1 F2 of 2, one can get 1 plus 1 by 2 is 3 by 2. Now, you can repeat this one, take the second composition of F1, F1 of 2, you can get 1 by 2. So, if you are applying F2 on 3 by 2, one can get this 1. So, and so on. If you continuing this process, in particular iterate of 2 generate point whose image under the repeated applications on F1 accumulate to the 1. If you are taking this one, it is accumulate the points with the 1. If both the points are accumulated with the nearest point 1. So, while generating this fixed point or fractal by using this condensation set, along with the number 0, 1, it will accommodate the some points near to 1. So, the attractor consisting of this attractor F1, F2 is only has the attractor 0, 1. Whereas, if you are adding the condensation set, it will consisting of the attractor 0, 1 from the standard IFS without condensation set and additional point generated from 2, that means the singleton set 2 forming a sequence that accumulate near 1, because the both the mapping, if you are applying in the both the mapping frequently on 2, one can get the point near 1. Hence, the attractor is no longer purely self similar, because there are some additional force and additional points we are generating in the each iteration. So, it is not as a self similar, but include a forced component coming from the condensation set. The extra element we are adding from the condensation set. So, here you can think we are adding the flavor of partial self similarity, because the finally attractor is the satisfying the self referential equation. So, what is the intuition? The usual iterated function system build a fractal purely from repeated contractions. A condensation set C act like a permanent seed or extra mass that is inserted at every iteration. Thus, the attractor is partially self-similar generated by the mapping Fi, and one more, the partially forced coming from the condensation set C, because there are some external force we are adding, therefore, the resultant attractor no more the exact self-similar, it has the self-similar with partiality. So, that is partial self-similar nature. Now, we can choose some proper compact set and condensation map, then we can generate the some partially self-similar attractor, that we can call it as a fractals with partial self-similar nature. This fractal is also generated from the a special type of iterated function system, and we are defining the Hutchinson map and the fixed point of the Hutchinson map with respect to the iterated function system. Same like the standard iterated function system, one can choose the different space and different contraction, one can generate more partially self-similar fractals by choosing appropriate set or metric space or contraction, or simply change the contraction and condensation set, we can generate the more partial self-similar nature fractals. Okay, maybe I will repeat once again. So, by adding the condensation set in the iterated function system, we can generate the fractal with the partially self-similar natures. The difference between the standard iterated function system and the iterated function system with the condensation set is, the condensation set, the standard iterated function system will generate the fractal with the exact self-similar nature, whereas in the IFS with the condensation set generate the fractals with partial self-similar natures. Now, the question is, if we have the iterated function system, we can generate the fractals, that means that we can generate the deterministic fractals. What is the converse? Suppose we have the fractals, that means we have the fractals. Is it possible to construct the proper iterated function system for the fractal object? These are the questions. Now, yes, it is possible. We can try with the famous theorem called the Collage theorem. This theorem states that let x comma t be a complete metric space, take that element L belongs to H of x and epsilon is a positive real number, be given, choose an iterated function system with the condensation with the contraction factor between 0 and 1, so that the Hausdorff distance between L and the union of this mapping with respect to the L less than or equal to epsilon, where HD is the Hausdorff metric, then the Hausdorff distance between L and A is less than or equal to epsilon over 1 minus S, where this A is the attractor of the iterated function system, this one. Equivalently, the Hausdorff distance between L and A is less than or equal to 1 over 1 minus S times Hausdorff distance between L and union of Wn of L for all L belongs to HFS. What this theorem says, x comma d be a complete metric space. Now, we are selecting a set L belongs to H of x. This will be given to us, and for a given epsilon greater than 0, we need to choose the iterated function system such a way that the distance between we need to choose the iterated function system such a way that the distance between L, this is the given target L, and the union of Wn of L must be less than or equal to epsilon. As we know, this is nothing but the Hutchinson mapping f of, or this here we are using the Hutchinson mapping as W. So, W of L, I can use the Hutchinson mapping notation as f of L. So, the Hutchinson mapping f of L and L must be less than or equal to epsilon. Like that, we need to choose the iterated function system. Then we know that this iterated function system has a attractor A, then the distance between A and L, that means the distance between A and L is less than or equal to epsilon over 1 minus s, where s is the contraction factor of the iterated function system. So, it means that if we have the attractor L, the attractor is given to us, the attractor is given. Now, we need to construct the iterated function system corresponding to the attractor. So, for given epsilon, we need to choose some iterated function system such that the distance between, how to choose the iterated function system, the distance between the target attractor and the union of Wn of L must be less than or equal to epsilon. Then, as per the Banach's fixed point theorem and deterministic fractal IFS theory, this iterated function system obviously will generate one attractor. The distance between the attractor and the targeted attractor will be less than or equal to this time. Whenever this epsilon, choosing proper epsilon, we can get that L is the distance between the L and A is very closer. That means that iterated function system may produce the similar attractor. So, for that we need to choose the proper epsilon and the iterated function system. So, the proof of the theorem is follow from this lemma. Let x comma d be a complete metric space. Let f from x to x be a contraction mapping with the contraction factor s, and the fixed point of f be xf. It is also belongs to the set x. Then the distance between x and xf, the distance between any point in the x and the attractor is less than or equal to 1 over 1 minus s time distance between x and f of x. F of x, that I need to check, sorry, x and f of x. Now, the distance function d of a comma b for any a belongs to x is a continuous in b, because distance function is uniformly continuous. Hence, distance between x and f of x can be written as distance between x. So, this is the attractor of f. So, the attractor of f is f of xf equal to xf, that is the fixed point. So, for fixed point as per the Banach theorem, this fixed point can be generated as limit n tends to infinity f of nth composition f of x, you can take, you will get xf. If you can take any random point and do the nth iteration, whenever this n tends to infinity, this point will converge into the xf. So, instead of this xf, one can choose the x this time. As the distance function is uniformly continuous, as we proved in the previous lecture, we can take this limit as outside. So, limit n tends to infinity, distance of x and f of x, nth composition of x, which is less than or equal to, here we are taking x and f of x. Here we can take summation m equal to 1 to n, distance between f of m minus 1 composition of x and mth composition of x, whereas distance between consecutive two distance. By using the triangle inequality, we will get this result. Again, here we can take d of x fx as common, then this is f is a contraction mapping with the contraction factor s. So, in each s is less than or equal to this one, each s is less than or equal to distance between f of m minus 1 of x, f of mth composition of x is less than or equal to some s times d of f of m minus 2 of x, f of m minus 1 of x. So, as per the contraction, we can take one by one. If you continuing as the n minus 1 state, then one can get limit n tends to infinity, distance between x and f of x can be written as this one. Then this is less than or equal to 1 over 1 minus s. Whenever this tends to infinity, the geometric series converges. This is will become, whenever n tends to infinity, one can get 1 plus s power 2 plus and so on. This is the geometric series, it will converge 1 over 1 minus s, since here s is the less than 1 and greater than or equal to 0. So, it will convergence to the 1 over 1 minus s times distance between x and f of x. So, this complete the proof of this one. The similar proof we can apply and prove that the Collage theorems. Now, we will discuss the example related with the Collage theorem. Now, we can choose one attractor and try to find the iterated function system corresponding to the attractor. Consider the target set L. So, this is my attractor. Now, I need to find the iterated function system corresponding to this attractor, that means the target set. So, for that I am choosing two mapping W1, W2 as like this one. This is my W1, this is my W2. Each map has the contraction factor 1 by 3. One can easily verify both have the contraction factor W1 of x minus W1 of y, which is equal to 1 x by 3 minus y by 3, which is equal to 1 by 3 of x minus y and easy. There is a similar manner one can prove this one, it has the contraction factor 1 by 3. Now, I have the two mapping W1, W2 and yes, the contraction factor is 1 by 3. Now, the Collage theorem says that you can find what is the W1 of L. That means, you can apply this mapping W1 on L and apply W2 on L. If you are applying W1 on L, one can get 0, 1 by 3. If you are applying W2 on L, one can get 2 by 3, 1. Remember, these two iterated function system we used to generate the Cantor set. Now, the same iterated function system we are using for approximating the L. Now, W1 of L is 0, 1 by 3 and W2 of L is 2 by 3, 1. Then if you are taking the union, we will get the middle part is removed, we are getting 0, 1 by 3 and 2 by 3, 1. Now, there is a gap, that means we are removed 1 by 3, 2 by 3. So, the distance between, because here we have the 0, 1, while applying these two maps W1 and W2. So, W1 we are getting here 1 by 3 and here 2 by 3. So, we have the gap here, we have the gap here, this is the gap for us. Now, this is the open interval. So, now we need to find the Hausdorff distance between L and the union of I equal to 1 to 2 W I of L. We need to find the distance. For finding the distance, first we need to find, because this part is removed, this union is contained in the set 0, 1. So, if you are find the distance which is equal to 1 by 3, the set 0, 1 by 3 union 2 by 3, 1 and find the distance union of these two set with the whole interval. If you are finding the distance one can get, it is an 1 by 3, this is the gap. So, Hausdorff distance measure the distance between the whole set and this gap, this two set, this is the gap. So, 1 by 3 is the Hausdorff distance. Now, so apply the Collage theorem. So, what is the Collage theorem? Here Hausdorff distance between L and A is less than or equal to distance between x and L and union of L 1 over 1 minus s. So, here we obtained that the Hausdorff distance between L and the union of L equal to 1 by 3. Now, this one you need to multiply with 1 over 1 minus s. So, this series 1 you can get, if you are applying this 1 by 3 is the ratio 1 over 1 minus 3 and this is the Hausdorff distance. So, 1 over 1 minus 3 because the contraction factor is 1 by 3 and the Hausdorff distance is 1 by 3. So, finally, one can get 1 by 2. That means the distance between L and A is less than or equal to 1 by 2. Now, we know that the iterated function system, the given iterated function system generate the attractor as a Cantor set. It is not equal to L, whereas the distance between the target set L and A is less than or equal to 1 by 2. Now, one can understand we are choosing these two iterated function system to approximate the target set L. That means, these two contraction mapping will give the iterated function system. By using the iterated function system, we will get the attractor and we are finding the distance between the attractor and the target set L. That L we are getting as 1 by 2, because this set, this contraction mapping generate the Cantor set, not 0, 1, whereas the distance between the Cantor set and 0, 1, the Hausdorff distance we can get after the first iteration, we are getting 1 by 2. So, one can choose some other contraction mapping to generate the proper target attractor. So, this is the way one can find the approximate for the given target set. It means that we can approximate the given set by the attractor of the IFS. So, this is the Collage theorem says. So, these are all some references one can refer. Thank you.